we look at the periodic table, we can get a lot of information based on where a particular element is in the periodic table. So whenever we talk about the periodic table, there's a couple terms that we want to look at. The first is going to be called a period. So period are going to be the rows in the periodic table, and the columns are referred to as the groups. So frequently we'll talk about a group number. We'll say all of the particular elements in a particular group number have certain characteristics. So again, groups are going to be the columns, and those are probably more important than the periods in terms of looking at an element and their chemical properties. So in looking at the periodic table, the main group elements are going to be in the groups that are numbered 1A to 8A. So if we look at the periodic table here, so here's 1A, here's 2A, then we skip the stuff in the middle, and then we go over here to 3, 4, 5, 6, 7, and 8A. Now, different periodic tables are actually numbered a little bit differently. This particular periodic table has kind of both sets of numbers. So sometimes it refers to as 1A, 2A, 3A, all the way up to 8A. And then sometimes it just numbers 1, 2, and then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, then 13, 14, 15, 16, 17, and 18. So the one thing to remember there is if you don't see the A after the name, you basically just have to subtract 10 from the ones that are over here. So 13 is just like 3A, or 14 is 4A. I'm not going to ask you like really any details where you need to know the difference between the A or whether it's not the A. I'm going to talk to it more in terms of particular groups and kind of what they're called, and you'll get a better idea of what I mean by that in just a second, I think. So for instance, main group elements are going to be the ones that are in basically shaded in blue here, right? So the main group elements are going to be the ones over here and the ones over here, and these are going to be your 1A through 8A, or 1, 2, and then 13 through 18, depending on how you want to look at it. The transition metals are going to be the ones in the middle. So again, I'm not going to refer to these as, groups 1B through 8B. I'm going to refer to them as transition metals. And the transition metals are going to be kind of these ones right here in the middle that are in gold. Or again, all of these are going to be metals. These ones are called transition metals. And then intertransition metals are these ones shown down here, which we're not going to talk about at all besides right now. And if you look at the periodic table and you look right here, see how there's a little gap? Kind of, it goes 57 then to 72, and then 89 then to 104. So if you kind of imagine this periodic table being in 3 dimensions, it's almost like these lanthanides and actinides, which are your intertransition metals, kind of pop out from the periodic table at that point, and then this extra row to them. Again, that's something that hardcore chemists look at and study. Nothing we're going to worry about at all in this class, so don't even worry about those. All right, so the most important thing here is understanding that columns are referred to as groups on the periodic table, and you want to make sure that you kind of understand the difference there between the period, which is a row, and the groups, which are the columns. Groups 1A and 2A, those two on the left side of the periodic table, are referred to as alkali metals and alkaline earth elements. You don't need to know those names or anything. Just know that they're metals and they have properties that are characteristic of metals, like they're solids, and they're going to have be good conductors of heat and electricity, right? So that's really all you need to know about those for now. Now, these names I want you to pay a little more attention to. So halogens are going to be important. We're going to talk about halogens quite a bit. They're very reactive, so in particular, whenever we start looking at chemical reactions, these ones are going to show up a lot. So these are the ones in group 7A. Now, the ones in group 8A, which are actually right next to the halogens, are going to be the noble gases. And these ones are very non-reactive, so they're very stable and don't react often at all. So I will frequently refer to the halogens, and I'm going to frequently refer to noble gases. So you should know whenever I'm talking about those terms where they are on the periodic table. So let's just go and look right here. So these ones right there are going to be the halogens. And these ones over here in group 8A are going to be your noble gases. All right? So those are going to be important parts of your periodic table to know. So fluorine, chlorine, bromine, iodine are your halogens. helium, neon, argon, krypton, xenon, radon, those are going to be your noble gases, right? So those are ones that you should definitely be able to pick out or kind of know what I'm talking about if I mention a halogen or a noble gas. All right, so moving on to electron structure. A lot of stuff that we do here in chemistry is very related, can be very related to physiology, right? We talked already about elements that are important in forming amino acids or proteins and DNA and things like that. A lot of the measurements can be related to kind of medical practices and things like that, right? Grams and dosages of drugs and things like that we looked at in chapter 1. This is one of those things, electronic structure, that you just need to know for this chemistry class. So I'm going to try to keep it as simple as possible to kind of get you through what you need to know. But this is just something that because you're in a chemistry class, you have to learn. I really can't link this to nursing or kind of public health or anything like that in any easy way. Now, one thing that kind of is important is this very first statement here where it says that the chemistry of an element is determined by the number of electrons in the atom. So the electrons are specifically what make an element react or kind of do all the work. The protons and the neutrons that stay in the nucleus, they're not involved really in the chemistry in terms of like an element's reactivity. It's always going to be in the electrons. Now, so talking in the electrons don't move freely around in space. Like we talked about that electron cloud and kind of into the structure of an atom. So even though the electrons kind of have that really large cloud, they occupy very specific energy levels within that cloud. So we'll talk about this a little bit more as we go through and talking about electronic structure. But again, picture your electrons kind of almost orbiting like planets orbit the sun in the solar system. They can go far away from the sun, which is going to be like our nucleus, where the protons and the neutrons are. But those electrons, as they go further away, are going to kind of be in these particular shells, right, or principal energy levels, right, which are going to be the regions that the electrons occupy, right? And these shells are going to be numbered 1, 2, 3. Kind of the larger the number, the further away they're going to be from the nucleus. So again, I like to use the analogy of the solar system. So picture the sun kind of in the middle, and that's going to be where the nucleus is. That's going to be your protons and your neutrons. The electrons are going to be like your planets. Mercury and Venus are the closer ones, right? The Saturns and the Neptunes are going to be the further ones away. The lower the number, the closer they are to the nucleus. When we look at these shells, which is going to be where the electrons go, the further away they are from the nucleus, the more electrons they can hold. And kind of one way to think about that is if you have the nucleus kind of here in the middle, right? The first shell is going to go around like this. The second shell is going to be further out. The third shell even further out. So you can see that as I get further and further out, the overall volume increases so it can hold more electrons, right? So the number of electrons is going to increase. Don't worry specifically about these numbers 2, 8, 18, and 32. I'm going to explain it a little bit differently on subsequent slides that are going to get to those numbers just in a different way. Everything that we do is really going to go only in shells 1, 2, 3, and 4, and we're only going to very briefly touch the fourth shell. So most of the stuff we're going to do is going to be in 1, 2, and 3, just a little tiny bit in 4. But again, I just want you to understand why the numbers in a number of electrons in a shell increase. And that's just because there's more room to hold it as those shells get further and further away from the nucleus. So if all of this isn't confusing enough, these shells are actually divided into subshells. And these are going to be identified by the letters S, P, D, and F. So while all of that is true, in terms of what we're doing in class, you don't even have to worry about D and F. You only need to know about the S and P subshells. D and F subshells exist. For the level of chemistry we're doing, we're not going to touch anything that goes into the D and F subshells. It just makes it a little bit more complicated, and we're not going to go there. So shells are the bigger things. Subshells are going to be kind of these regions within an individual shell that contain the electrons. Those electrons are found in orbitals. So orbitals are found within the subshells, which are found within the shells. And then the electrons are inside those orbitals. So an orbital is specifically defined as a region of space where finding an electron has a high probability. And those orbitals hold 2 electrons. So if all of this isn't making sense, by the way, bear with me for like another minute or two, and I'm going to get to doing kind of some problems where I think just by doing the problems, it's going to make a little bit more sense. So here, if you look at the subshells, right, we're going to add electrons in terms of increasing energy. So we're always going to start by adding electrons at the lowest energy, moving up to the higher energy. So again, we don't even really have to worry about D and F. So we're always going to add the S, fill up the S subshell of subshell first, and then the P subshell. The S subshell only has 1 orbital, so when it has 1 orbital, it can hold 2 electrons. And I use this E minus symbol to talk about electrons. It's like an electron, and then the minus just is like a reminder that electrons have a negative charge. The P subshell, because it has 3 orbitals, if each orbital can hold 2 electrons, the P subshell can have a total of 6 electrons. Right? So those are going to be kind of important numbers as we move forward here. Okay, so here is kind of where we start to put all of this together in terms of being able to look at an element and write its electronic structure or its electron structure. Shell number 1 has a 1s orbital, right? So basically 2 electrons can go into this 1s orbital. After the first shell, you don't have room for any more electrons, and then you have to go out to the second shell. Well, in the second shell, you have both s and you have p orbitals. So now you have a 2s orbital, and then you have 3 different 2p orbitals. Because remember, in our p subshell, right, we always have up to 3 orbitals. So that's why anytime you have the p here, we have 2p, 2p, 2p. The reason that this is shown 3 different times is each one of those 2p's can hold 2 electrons. And that's why we get to this number 6 over here within the 2p. Overall, in the second shell, we can have 8 electrons. 2 from the 2s, and then 6 from the 3 separate 2p's. That adds up to 8. Now, whenever we go out to the third shell, that's when we would actually include the d orbitals as well. You can actually have up to 10 there, and that's where we would get to that number of 18. If we went all the way out to the fourth shell and we start adding in the f electrons as well, that's why that number would go up to 32. And again, we're not going to quite worry about going that far. All right, so the electron configuration of a given atom says how the electrons are going to be arranged. So we're going to look at writing out what's called the ground state electron configuration, which is going to be the lowest energy arrangement. And there's a whole lot of words on this slide, and I just kind of want to point you to this rule 1, where it says electrons are placed in the lowest energy orbital, starting with a 1s orbital. And then going to the rule 2, which says that each orbital holds a maximum of 2 electrons. Those are kind of the 2 take-home points to this. So I want to go to the next slide here, which talks about kind of how the energy levels increase. So you start with 1s, then you go to 2s, then you go to 2p, then you go to 3s, then you go to 3p, and then I'm going to draw one more on here because we need to be able to go up to 4s. Now, a lot of times people will say, well, what about the D ones? Why don't we worry about 3D? How come you're going straight to 4s and not 3D? And the reason is, if we were to add 3D on this chart, 3D actually goes above 4s. And this is why I say it gets complicated, right? So you actually go 4s, then 3D, then 4p, and it gets a little bit complicated. So because of all of that, I'm going to erase 3D because you don't need to know that, and you need to know that after 3p comes 4s, and beyond that, we don't have to worry about anything in terms of what we're doing in this particular class. Okay, so here is kind of how this looks whenever we talk about it. If you were to say, write the electron configuration for hydrogen. Hydrogen has a total of 1 electron. So your job is to put that 1 electron in the lowest orbital possible to have it the lowest amount of energy. If we look at this chart, the lowest amount of energy is in the 1s orbital, so we're going to put it there. So one thing I should probably add to this figure here, in 1s we can fit up to 2 electrons. In 2s we can put 2 electrons. In 2p, right, remember in p we have 3 orbitals, so we can fit a total of 6 electrons anywhere that we have p. Anywhere we have s, like 3s, we can fit 2 electrons. In 3p we can fit 6 electrons. And then 4s, again, is an s, so it gets 2 electrons. So if we added up all of these, 2 plus 2 plus 6 plus 2 plus 6 plus 2, that would get us up to 20 electrons. So basically, what I'm asking you to be able to do is write electron configurations for elements that have up to 20 electrons. Right? Beyond that, we don't have to worry about. Okay, so hydrogen, 1 electron, it goes into 1s. Helium has 2 electrons, so now we would say 1s2. The superscript here refers to the number of electrons in that 1s orbital or subshell. So if we were to look at carbon down here, it says 1s2, 2s2, 2p2. That number 1 refers to the shell, right? And that number 2 would refer to the shell, and that 2 refers to the shell. The s and the p, those are going to be the subshell. So the subshell refers to that s, or that p. And then the number of electrons in each of those subshells is where the superscript refers to. So I'll draw the arrow going this way. So that's that 2, or that 2. All right, so for carbon, the 1s2, 2s2, 2p2. Again, we go to 1s2 first. After we put 2 electrons there, it's all the way filled up. And then we still have 4 electrons left, right, because carbon has 6 total. The next 2 go into the 2s2 subshell, or in the 2s subshell, we put 2 in there, and that's all it can hold. And then we still have 2 more, and then we go to the 2p. So again, whenever you're doing the electron configuration, if you basically memorize this, and I need to re-add my 4s on there, and you have 2 electrons down here, 2 electrons here, 6 there, 2 there, 6 there, and 2 there. If you can remember this, you basically start down here at the bottom and you just work your way up, not to exceed the maximums that are there. You should be able to write out these electron configurations. So let's do an example one. So here, what is the electron configuration for aluminum? So we go to the periodic table, we can find aluminum right there. Okay, so that means because its atomic number is 13, it has a total of 13 electrons. Right, so we have to start placing them in order. We start with 1s, because 1s is always where we start, and we know we can fit 2 in 1s. Right, so now we have 11 left. So then we go out to 2s, and we say 2s, 2, and now we still have 9 left. So now we go on to 2p. So 2p can hold up to 6. Then we run out on 2p, so that's a total of 10. And then we go to 3s. And we know that anytime we have an s, we can go up to 2. So now we're up to 12 total. So that takes us to 3p. And we put 1 more there. If we add up all of those numbers that are the superscript, we get 13, which is our 13 total electrons here. And while I'm on this slide, I kind of want to point out something else because I think it's kind of helpful to look at it this way. Anytime you have something that, well, let me not write it that way. Let me, if we look over here at group 1A, these ones are always going to end in S1. So hydrogen is going to end in 1s1. Lithium is going to end in 2s1. So notice the shell is basically the same as the period number on the periodic table. So if we were doing just hydrogen, it would be 1s1. Lithium would end in 2s1. Sodium would end in 3s1, 4s1 for potassium, 5s1 for rubidium, 6s1 for cesium. Okay? The ones in group 2A are always going to end in group 2, in S2. So beryllium is going to end in S2. Magnesium, calcium, strontium, they're always going to end in S2. Now the other one that's kind of tricky that ends in S2 is helium, right? And it moves over here on the right of the periodic table because it's a noble gas. But you could almost imagine it would go right in this spot there as well. So we can refer to these ones here as S-block elements. So they're called S-block elements because the last electron that goes in is going to end up in an S subshell somewhere. These ones over here are going to be called P-block elements. So these ones are going to end in P. So for instance, anything that's in group 3A is going to end in P1. That's what we just did for aluminum, right? Boron would be the same way. And then it's going to be P2. These ones are going to end in P3. These ones are going to end in P4, P5, and then the noble gases are going to end in P6 with the exception of helium. So again, helium's the exception. It can't have P6. It only has a total of 2 electrons anyway. Right? But for neon, argon, krypton, xenon, radon, those ones are always going to end in P6. Now, we're not talking about them in our class, but all of the transition metals in the middle, these ones would all be D block in the middle. And then the lanthanides and actinides, those would be F block. So if you ever hear that terminology, right, that's what it means. And all it means is it's where it's going to end on the periodic table. So we just did aluminum, and we said it ended in 3p1. If we were to want to do boron, boron would be the same thing, except it would end in 2p1. Gallium would end in 4p1, right? The 4 because that's where the last, the period is on the periodic table. And then p1 because it falls in this range here. So again, that's just another way to kind of look at all this stuff that kind of might help you understand it a little bit better. All right, so if we were to try to find the electron configuration for magnesium, so we go down here and we find magnesium. It has 12 electrons. So this one is very similar to the aluminum that we just did. It just has one less electron. So we can tell before we even start that we should end in 3s2. But in order to get to 3s2, we first have to fill up all the other ones. 1s2, and then we go to 2s2. So 1s2 takes care of this electron and this electron. 2s2 is 2s1 and then 2s2 here. And then after 2s2 is going to come 2p6. So this would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. And then we go down to 3s1 and then 3s2. So that's going to be 3s2. So that would be the electron configuration for magnesium. All right, and then lastly, looking at it a different way, what element has the following electron configuration? 2 different ways you could get to this one. First, you could say, okay, it ends in 3p5. So we just talked about that the ones over here in blue on the right are going to be where our p electrons is. 3p5, so this is 1, 2, 3. And then basically this would be 3p1, 2, 3, 4, 5. So this is going to be chlorine. All right, so this is going to be chlorine. Now the other way to look at that is if we counted the total number of electrons, looking at the superscripts here, right? We have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17. We know that there are going to be 17 total electrons. That means it has to be chlorine, right? So 2 different ways to get to the same answer for this one. So again, you should be able to take an element up to calcium, right, and write the electron configuration for it. Calcium would end in 4s2, and you should also be able to look at an electron configuration and determine what element it is.